everybody. Today we're going to be talking about section 3.8, which is on human population dynamics. And I'm going to talk about a theory introduced by an English economist from the late 1700s named Thomas Malthus. So that's why I have a picture of this guy on the beginning slide, but I'll explain his theory in a second here. First of all, we're going to start out with the learning objective. And learning objective for today is going to be that you can explain how human populations experience growth and decline. We're going to talk about things like birth rates, infant mortality rate, death rates, and different developed and undeveloped components that can play into this, such as the affluence of the country. We're also going to talk about the human carrying capacity and things that impact this for the whole world carrying capacity. We're going to talk about some different equations that we can use to calculate growth rates and how long it's going to take for populations to grow at a certain amount. And you're going to practice the suggested skill of describing environmental problems. So the question that many people have asked is, does Earth have a human carrying capacity? And Thomas Malthus, the guy whose picture was on the first slide, had what's called the Malthusian theory. And basically what he theorized is that Earth does have a human carrying capacity, and it's probably going to be based on food production. And he believed that the human population growth is happening faster than the growth of food production. And so humans will eventually reach a carrying capacity here on Earth that will be limited by food. So if you look at the top graph on the right-hand side here, we're showing the population growing. We're seeing the amount of population that can be fed by food supply, and eventually we'll hit this point where we cannot make enough food to feed the population. However, what Thomas Malthus did not take into account was this idea of technological advancements and how those can impact our potential carrying capacity. So humans are very different from other species in the fact that we can alter our carrying capacity with technological innovation. Now, an example of this is going to be how in the early 1900s, scientists figured out how to do fixation of nitrogen in a way that can be used for synthetic fertilizers. And once we started having synthetic fertilizers, this dramatically increased the food supply, and it increased the amount of food that we were able to grow on our farms. So if you look at the bottom graph here, it shows the same growth curve of the population and how much population could be fed by food supply. But if you look at when we had this jump in fertilizer, that innovation then changes this graph in a way that we can create more food. And so we are pushing off the potential for when we're going to reach that carrying capacity, especially in the fact of it being limited by food, because most economists and biologists do believe that food is going to be our limiting factor here on Earth when it comes to the carrying capacity of humans. So if you look at this diagram here, it shows us how we can have exponential increases in our food supply by these technological advances. So if you look over time, this is the long-term cereal yields, which are going to be like grain yields in the United Kingdom. So if we look all the way back for hundreds of years ago, it was fairly consistent in what we could produce. And right about here is where we get that synthetic fertilizer ability. And we see the ability to grow skyrocket here. And this is the kind of thing that technological advances can do for us. So although there are still economists and biologists who have certain theories for the maximum carrying capacity that we have as a human population, it's way harder to predict this because we can't know what kind of technological advances we're going to have in the future and how that's going to impact our food creation abilities. And so just keep that in mind. Most people do believe there is an ultimate carrying capacity for humans, but we can't really predict it because who knows what's going to happen in the future. We might see more things like this, like what we saw with synthetic fertilizer. But when we are talking about the growth rate of a population, there's a few different factors that can go into it. And I'm going to introduce you to a little bit of math here for how we can calculate some of this. So when we talk about growth rate, it's often referred to with a lowercase r. And this is going to be the percent increase in a population. And usually we look at it per year. So for example, if a population has a growth rate of 5% of 100, that usually means that they're going to grow to 105 individuals. And the things that go into growth rate are going to be your crude birth rate and your crude death rate, which are going to be your CBR and your CDR. And these they are always going to be the births and deaths per 1,000 people in a population. So for example, if we were to have a global birth rate of 20 and a global crude death rate of 8, that is going to give us the equation that you see on the bottom here. Now, because we have births and deaths per 1,000, and that's how it is shown, it actually makes it pretty easy for us to get to a percentage. You just have to remember that we need to divide by 10, because if it's out of 1,000, to get it to out of 100, you divide by 10. So this equation that we're going to see here is the crude birth rate minus the crude death rate divided by 10, because you want it to be in a percentage. And so we're going to do 20, which is the number we were given up here, minus 8 divided by 10, which is going to give us 1.2%. Now, growth rate is always going to be expressed as a percentage. So that's why if we're starting with out of 1,000, we divide by 10 to get us out of 100, and then make sure you always want to keep those units right, that you're going to be showing it's a percentage after this equation here. So that's how you're going to calculate the growth rate of a population. Now there's another equation, and it's called the rule of 70. And the rule of 70 is going to tell you how much time it takes in years for a population to double. And basically the way that you are going to calculate that is through this equation, the rule of 70 formula. The doubling time is going to be equal to 70 divided by the percent of growth rate. So if we look at the example that we just calculated on the last slide, if we have a growth rate of 1.2%, the way that you would find the doubling time is to do 70 divided by 1.2, which is going to give us 58.3 years. So the global population will double in 58.3 years by using this rule of 70 formula. So what I'm going to have you do is calculate with a practice problem. So if a country has a crude death rate of 9 and a crude birth rate of 18, I want you to first calculate the annual growth rate and then calculate the doubling time. So I'm going to have you pause the video here and calculate this, and then we will be able to unpause it so that I can give you the answer. Okay, so I'm hoping that you paused it so that you can compare the answer that you got to what I'm going to show you. So the way that we would calculate this, remember, you do the birth rate minus the death rate divided by 10 to make it a percentage. So we would do 18 minus 9 divided by 10, which is going to give us a growth rate of 0.9%. Now, in order to do the doubling time, we go to the formula for the rule of 70. So we would have 70 divided by that growth rate, which is going to get us to 77.77 years in order to double. And that's how long it would take this country for it to double its population based on the growth rate that it has right now. Now, this slide is going to be a bit of a recap of what we covered in 3.7. So I'm going to go through it kind of quickly, but I want you to keep in mind the different factors that can affect a human population growth, either globally or in a country. And so we're going to look at what can impact that growth and what can decrease that growth. So the things that increase the population growth are going to be a higher total fertility rate, which means you have a higher birth rate, that crude birth rate, which is part of our equation here. Now, additionally, the high infant mortality rate can drive up the total fertility rate because of the replacement children. So that's going to be something that will factor into our birth rate and also our death rate. The ones who died are going to be part of that. Another thing that can increase population growth is going to be high immigration levels. Additionally, increase access to clean water and healthcare. this tends to decrease death rates, which I went into that in depth in our 3.7 notes. So you can revisit that if you aren't quite sure why clean water and healthcare will impact death rate. Now, the factors that are going to decrease your population growth are going to be a high death rate or a high infant mortality rate, because those are going to be factors that go directly into that crude death rate right here. Now, also, as we talked about in 3.7, increased development is going to lead to a decreased total fertility rate, which will decrease that crude birth rate. And then we are also going to have increased education for women can decrease the population growth, because this leads to delayed age of first child and postponement of marriage age. And again, I explained all of that in 3.7, so you can go and revisit those if you need a little bit more of a connection of why that ties to a decreased population growth rate. But these are all going to be factors that are ultimately going to go into the numbers that we're seeing for that crude birth rate and that crude death rate. And so overall, it's going to impact the growth rate of human populations. Now, we also have these different factors that we can look at, and they're called standard of living indicators. So what is standard of living? That is basically what is the quality of life for people in a certain country. And there's going to be a few factors that tend to go into these. And the first one is going to be the gross domestic product, which is the GDP. And this tends to be a key economic indicator of standard of living. And the GDP is essentially the total value of the goods and services produced by that country. And then we take it per capita. So we go and we divide it by the total population to find out if we were to take the entire wealth of that population and divide it per person, if you have a higher per capita GDP, that's going to tend to mean that people have more income and they're going to tend to have a higher standard of living. Now, life expectancy is also going to be a key health indicator of standard of living because, first of all, this life expectancy, basically what I mean by that is it's just the average age a person will live to in a given country. And life expectancy is going to increase when you're getting access to things like clean water, healthcare, stable food sources. And what we see is if you have a country that has a high GDP and a high life expectancy, then those are going to be places where we tend to see a better standard of living. And GDP and life expectancy are both going to be indicators of development. So areas that have high GDP and high life expectancy are going to be more developed countries, and they're going to have lower population growth. So sometimes we can even see this correlation between standard of living and the population growth that we are seeing from that country, because those do tend to be connected to each other. Again, I did cover some of this in 3.7, so you can revisit those for a little bit more in-depth coverage of this. So this is going to be your FRQ practice 3.8, where you're going to practice the skill of describe environmental problems. So I want you to describe one environmental problem associated with a rapidly growing human population and propose a solution that a government could take to slow population growth. And you might need to revisit 3.7 because we did talk about some of these strategies in 3.7, but here you're going to tie it to an environmental problem. So that's going to be your FRQ practice for 3.8, and those were your notes on section 3.8 about human population growth.